Good morning, everyone. Thank you for joining this presentation today. First of all, I would like to introduce myself. My name is Stefani. I'm 30 years old and I'm from Munich, Germany. I worked as an IT consultant since 2014, which is my full-time job, and in 2018 I decided to do a master's degree in artificial intelligence. Last summer I graduated with distinction, and during that time I also met a lot of great people, especially my two colleagues, David, who was my supervisor for my master's dissertation, and Rushanek, who was my co-supervisor. So essentially both of them are the reason why I'm speaking to you today, and I'm very happy about it. So let's start. Today I would like to talk about our network named AutofocusNet for brain tumor segmentation MRI, which is an easy to use and publicly available network implemented with NiftyNet. And as far as I know, as researcher in the field, you will appreciate that very much. So to make it clear what we did, I've divided my presentation into 5 parts. First, I talk about the background and purpose of our work, then our network AutofocusNet and how it was developed. After that, I'll show you some segmentation examples. Then I will show you quantitative results achieved with our network, and finally a brief summary of what I talked about today. Let me begin by discussing the motivation which gives us an answer to the question why brain tumor segmentation is so important. First of all, according to the NHS, there are over 11,000 people per year in the UK diagnosed with primary brain tumors originating in the brain. And beyond that, there are many others diagnosed with secondary brain tumors. In this work, we're focusing on glioblastoma, GBMs, which is the most common aggressive form of primary brain tumors. There are 2 types in the dataset we used: low-grade gliomas, LGG, which are benign and slow-growing, and high-grade gliomas, HGG, which are malignant and fast-growing and way more aggressive with worse prognosis because treatment is difficult due to their characteristics. To improve survival rate, brain tumor segmentation is an important task used in diagnosis, treatment planning, and treatment. This means that the location and size of the tumor needs to be determined, and also the tumor boundary needs to be precisely outlined, because when radiotherapy will be used, you want to expose as little healthy tissue to the radiation as possible. Further, the treatment process needs to be monitored because, of course, you would like to know if the radiotherapy is successful or not. However, the manual process might be error-prone. It also might be very expensive and time-consuming when carried out by humans. Just imagine if you ask multiple experts to mark the tumor regions in an MRI, everyone would mark the region differently, also varying in size. So for these reasons, automatic segmentation helps to address these problems and has the potential for accurate and reliable results to support precise treatment. However, this task has proven to be highly challenging and is the subject of this work. Okay, then let's move on to MRI. To segment tumors, experts can use MRI technique to create images of the brain, and with varying MRI sequences, it is possible to generate different types of brain images with different appearance, as you can see on the bottom left side. For example, in the FLAIR image, you can see the tumor core, that's the white region, pretty well compared with T1, because the MRI settings to create the FLAIR image make abnormalities very bright. Usually the generated scans are 2D because MRI looks at the brain in a series of images, which leads to multiple slices per plane. And the planes are first the axial horizontal plane, in which the MRI scans the brain from below to top. Second, the coronal vertical plane, where the MRI scans the brain from the back and moving to the face. And third, the sagittal longitudinal plane, where the MRI scans the brain from one ear to the other. What this means is putting the 2D slices on top of each other and combining all slices from all 3 planes produces a 3D model of the brain. One important point to mention is using all the different types of MRI images for training a network actually leads to better results, since they provide complementary information for different tumor subregions. Good. Now I would like to move on to image segmentation. In general, semantic image segmentation aims to associate each pixel in an image with a certain class, which allows a machine to recognize objects in an image. For example, a binary case in which a pixel belongs to one of 2 classes, tumor or non-tumor. And probably the most promising methods today are based on CNNs, which are the basis for networks that emerged over the last decade. Figure 3 shows an example architecture of a CNN. It usually consists of multiple convolutional layers to detect local conjunctions from features. followed by a pooling layer to merge semantically similar features into one. And this arrangement can be repeated arbitrarily. Typically, the last few layers are fully connected layers, as in regular neural networks, to classify objects. The advantage of CNNs is that this hierarchical feature representation makes it possible to learn representations of features solely from raw data. This means it automatically detects the important features without any human supervision. For example, given many pictures of brain tumors, it can learn the key features which are important to detect tumors by itself. Let's take a brief look at automatic segmentation approaches. Examining the literature about medical image segmentation shows various machine learning methods. And a vast majority of 2D and 3D CNNs have been proposed, and there's still a lot of work going on in the field, finding even better networks. One example might be the annual BRATS challenge, but most of the brain images are 3D volumes today. Therefore, using a 2D network on 3D volumes might be suboptimal because you would have unused image information along the missing third axis. Due to unknown behavior of these brain tumors, not any current technique can visualize the tumor and related regions perfectly. Therefore, new designs can improve the segmentation results to understand this disease much, much better. This is also one of the main reasons that served as an inspiration for our work, which I'll present next. But before I do so, I have to explain what WNet and autofocus layer is. WNet is the first network of 3 cascaded networks. In the original paper, WNet was merely used to segment the whole tumor WT as in a binary case in the first step before passing the segmentation results on to the next network in the cascade for further processing. However, there was another paper in which a single WNet was also used for multi-class segmentation to segment all tumor subregions within one network at once. Basically, this was evidence for us that it's possible to train the WNet for binary and multi-class segmentation. In figure 5, the WNet architecture is shown, and it consists of 10 residual blocks in blue with anisotropic convolutions, dilated convolutions, and multi-scale prediction to improve the segmentation performance. Each of the 20 convolutional layers in a residual block is an intra-slice layer with kernel size 3 by 3 by 1. And the 4 interslice convolutional layers in orange have a kernel size of 1 by 1 by 3. This decomposition of a 3D kernel with size 3 by 3 by 3 into intra and interslice deals with that anisotropic receptive fields. Further, the 2D upsampling layers in red make sure that all dimensions of the tensors are from equal size when applying the concatenate operation at the end before the output. Autofocus layers can be integrated into existing networks by simply replacing standard or dilated convolutions. The key feature is that it adaptively changes the size of the effective receptive field to generate much more powerful features, which of course should lead to better segmentation results in the end. Taking a closer look at figure 6 shows that an autofocus layer consists of an attention model indicated by small letter A and K parallel dilated convolutions, each with a different dilation rate, which you can see in figure 6b. Here, K equals 4, and therefore we have 4 parallel convolutions in an autofocus layer. It is important to mention that the parallel convolutions must share the same weights to make the network scale invariant. In other words, the parallel filters share parameters which allow each filter for seeking patterns with similar appearance but different size. So this approach leverages the fact that the texture of large developed tumors compared to small tumors in an early stage differ to regularize learning. C shows an example of attention maps for the first 2 convolutions, R1 and R2, each with a different dilation rate. Here you can see how they choose the optimal scale for identifying different objects in an image. The red and blue arrows indicate which objects in the image are more relevant than others at the moment. Now I've explained 2 important bits and pieces necessary for our network, to which I will come next. Here you can see a representation of our AutofocusNet. As mentioned, AutofocusNet is made up of a modified version of WNet with incorporated autofocus layers. And how did we do that? All decomposed kernels of size 3 by 3 by 1 and 1 by 1 by 3 in the WNet were changed into more 3D shaped kernels with size 3 by 3 by 3 and 1 by 1 by 1 respectively. Then only the first 4 residual blocks in blue were kept, and the last 6 residual blocks converted into autofocus blocks in yellow. Each autofocus block consists of 2 autofocus layers with a residual connection as it was before. And each autofocus layer consists of 4 dilated convolutions, each with a different dilation rate, which you can see in figure 7, indicated by D/D/D/D in the legend below the network. Everything else was kept as it was in the original network. So the question is, why did we do that? As we saw, the WNet processes 2D/2.5D images due to the shapes of intra and interslice kernels. So in the first step, the adaptation from 2D/2.5D to more 3D shaped kernels was to change how the 3D MRI volumes will be processed. This adjustment makes sure we don't miss any information on the third axis and use the entire volume for training. And last, our proposed network incorporates 6 autofocus blocks, which is 12 autofocus layers, by replacing the last 12 standard convolutional layers. This was done because we wanted to enhance multi-scale processing of CNNs by enabling the network to select the appropriate scale for identifying different objects in an image. So that's how our network looks like. And on the next 2 slides, I would like to show you some segmentation results for a binary and a multi-class model. This image is a representative result of the model trained for binary case to segment the whole tumor WT in a given MRI volume. The network output from our model assigns a probability to each voxel volume pixel between 0 and 1, where 0 is blue and doesn't belong to the tumor region, and 1 is red and belongs to the tumor region. The green/yellow pixels are somewhere around 0.5 on the scale and is more or less exactly in between blue and red. But if you compare these results with the ground truth in column B, you can see this very close to this particular subject. This image on the other side is a representative result of the model trained for multi-class case to segment the whole tumor WT, enhance tumor ET and tumor core TC in a given MRI. Same as before, the network output assigns a probability to each voxel between 0 blue and 1 red. However, you can easily see that the segmentation result compared to the binary case is worse. One reason for this is, of course, that if you introduce more classes, the problem gets more complex. And so training a network is much harder as before, and particularly with the same amount of training images. Nevertheless, the network did a good job, because if you look at the different subregions, you can perfectly see the shapes of these subregions. So in general, the network is able to figure the differences out, even if it's not perfect. But I will talk a little bit more about this problem in my conclusion later. Moving on, the next slides will show you the quantitative results achieved with our networks. For comparison reasons, we use a typical metric called die-score, which measures the amount of spatial overlap between 2 image regions. In this case, the overlap between ground truth and the prediction of our network. We trained 4 binary models and 4 multi-class models. The models are 2D WNet, 3D WNet, 3D AutofocusNet with 3 dilated convolutions per autofocus layer, having dilation rates of 1, 2, and 3, and the 3D AutofocusNet with 4 dilated convolutions per autofocus layer with dilation rates of 2, 4, 8, and 12. As the name suggests, the pre-trained WNet 2D was pre-trained on the BRADS 2017 dataset for binary segmentation and was provided within the NiftyNet library we used. I listed it here because it might be good to see how our models perform compared to this. All our models were trained on a subset of the BRADS 2018 dataset because the original validation set comes without ground truth labels. It cannot be used for evaluation. Therefore, we randomly split the BRADS 2018 training set with 70% training images, 20% validation images, and 10% for making inferences on. In numbers, we had 199 training images, 57 validation images, and 29 inference cases on which we tested all our models for fair comparison. The generated validation set was used during training of all our models to tune the hyperparameters. Looking at the results actually showed that all the different models are very close to the provided pre-trained 2D WNet, but all 3D models perform worse with a much higher standard deviation. This slide shows the quantitative segmentation results across all models. However, it is difficult to compare the results with results in literature because they use a different trained test set. As I mentioned, we had to split the provided training set and therefore had much less images available for training our models. This means we trained our networks with approximately 30% less images, which is 86 images. For some of you, the training and inference times might be from interest, so that's what I'm going to show next. The training times across all networks using 199 subjects are measured in seconds, but to give you a feeling what this means without calculating it right now, all the models took about plus minus 30 hours. This is because each model was trained 3 times, every time with a different view. First in axial, second in coronal, and third in sagittal view. And then when making inferences on a previously unseen MRI, the MRI image will be processed by all 3 models, and the 3 results were combined to generate an average segmentation result, which leads to better performance than using merely the single results. Some people might ask why training the binary 3D AutofocusNet on the very top left in sagittal view was so much faster than the others. This was also my question once I saw the results, but it was just, let's say, a good day or a good time slot for the computing machine in the lab we used for our experiments. But basically, it had nothing to do with settings or images or whatever, because there were no changes made between training the models for axial, coronal, and sagittal view. This slide shows the time required for making inferences using the different models on 29 subjects. And if we divide the time required to make inferences for all 29 subjects, the average inference time required for just one subject would be about 27.34 seconds using the binary 3D AutofocusNet with the 4 dilated convolutions in autofocus layers, for instance. So in this presentation, I wanted to show you our experiments with our AutofocusNet and how it performs compared to similar networks. And to sum it all up, we used doublenet and adapted it from 2D to 3D and additionally replaced a part of the standard layers with autofocus layers. Our best binary model achieved at least similar results with a die score of 83.92% as the models proposed in literature. We trained our network on the Brett's 2018 dataset, but with approximately 30%, so 86 less images for training, which can be a huge setback in an area. Due to the compute and time constraints, we were unable to search through the whole hyperparameter space. This does, of course, highlight the need for further research in that area, and in particular into optimizing the hyperparameters and the autofocus layer settings, which includes the correct number of autofocus layers in a network, the number of parallel convolutions inside an autofocus layer, and the correct dilation rates, and so on and so on. However, we haven't exactly achieved similar results with the AutofocusNet compared to results in literature, but the experiments are still for importance because it appears that an increase in the number of parallel convolutions inside the autofocus layers improved the segmentation results of a model. This might be due to the capability of an autofocus layer to adaptively change the size of the effective receptor field and learn more powerful features, which might be crucial to segment all the tumor subregions precisely due to the complex tumor structures. Of course, the introduction of more and more convolutional layers makes a network more and more complex, which leads to increased training and inference times, but we believe it's even more important to make a network capable to identify and understand the tumor subregions better at the expense of time. Okay, that's all I got. Thank you very much for your attention. It was a pleasure talking to you today. And if you have any questions, please do not hesitate to contact me.